Okay, 9.6 is the last section in Chapter 9. We're going to start that now. We're going to talk about what's called complex numbers. One property of a real number is that its square is never negative. For example, there is no real number x such that you can square x and get -1 or any negative. So if we were asked to solve the equation x squared plus 1 equals 0, there would be no real solutions to that. Okay, and that would be just what we'd write down. Now, what we're going to do next is we're going to define a number that is a solution to that equation. Okay, here it is. Definition: the symbol I is the basic unit for what's called imaginary numbers, and it is defined by I squared equals -1. And I is defined to be the square root of -1. Okay. Earlier in the chapter, we talked about the square root of a negative, how that cannot be a real number, and that's true. But we're gonna get more clarity on that now. We're going to talk about these imaginary numbers. Problem 29 is where we're going to get some practice simplifying and writing expressions in terms of I. Okay, so let's take a look at part A, the square root of -7. What does that look like in terms of I? Well, -7 is the same as -1 times 7, and I know that I can split a radical as long as I'm multiplying or dividing things underneath. So I can go ahead and split this. The square root of -1, by definition, is what we're calling I. Root 7 would be still there, and so I root 7 would be the square root of -7, but now rewritten into an imaginary form. Okay, here's another one, part B, the square root of -16. Well, -16 is the same as -1 times 16. I can then split that radical into two. The square root of -1 is I. The square root of 16 is 4. So 4I would be my answer. Now, you could also write I times 4. That's the same thing. Multiplication is commutative, right? If I ask you 3 times 5, that's the same result as 5 times 3, okay? Usually, if we have an expression that does not contain a radical, like what we see here, we write I after the real number part, although you could write I times 4. That's the same thing. Usually, when we have an expression that does contain a radical, like we saw right here, usually we write I in front of the radical so that it doesn't look like I is underneath the radical, okay? If a student were to write the square root of 7 times I, that would be fine. You just want to make it look like I is not underneath the radical, okay? So to avoid any confusion, is I underneath the square root or not, we just write I in front of the square root, and then the whole thing is a non-issue. Here's another one, part C, negative the square root of -13. Well, I've got a negative in front of the radical. That's got to stay in front of the radical. The square root of -13, well, that'd be very much like these other two, right? The square root of -7 is I root 7. So the square root of -13, that would be I root 13. I would just have a negative in front of that since I had a negative in front of the square root sign. Same deal here. Okay, negative the square root of -48. Well, the negative in front of the radical would have to be kept there. The square root of -7 is I root 7, so the square root of -48 would be I root 48. Again, I've still got the negative there. Now, root 48 is also going to simplify, okay? If we look at 16 times 3, that's 48. That would be the best pair of numbers because we know that the square root of 16 is 4. So 4 root 3 would be the simplified form of the square root of 48. My answer then, in terms of I, would be -4I root 3, okay? So that's just dealing with imaginary numbers. Now the section is called complex numbers. Let's define that. Okay, definition. A complex number is a number of the form a plus b times I, where a and b are real numbers and I is the imaginary unit. That is what we were talking about before. I is the square root of -1. Okay, now up to this point, everybody in the world learns about our number system the same way. You know, like when you first start working with numbers, you talk about natural numbers. Natural numbers are counting numbers. And then you'll learn about negatives, right? Counting numbers in their negatives are called integers, so you have to make your current set of numbers bigger. And then you learn about fractions. Rational number is just a fancy word for fraction, okay? So you gotta, make your current set that you've learned bigger now to throw in all these fractions. And then you learn about numbers that cannot be written as fractions. We call those irrational numbers. Pi would be an example of an irrational number. There is no way to write pi in fractional form, okay? The square root of 2 would be another example of an irrational number. There's no way to write that in fractional form. Now, if you have the set of rational numbers, fractions, and also the set of real numbers, ones that are not fractions, and you throw them all together in a big pile, we call that the set of real numbers. Okay, all the rational numbers and irrational numbers make up the set of real numbers. A real number is basically any number that you've ever seen in your lifetime. Okay. Yet again, we're going to have to make our current set of numbers bigger in order to throw in these complex numbers. Okay, now the natural question next is, why do we care about all this? Like, what's the point? Okay. Well, we're going to see in the next chapter, and beyond that sometimes we're going to run across the square root of a negative, and we're going to have to deal with these calculations. Okay, so we're going to have a plan in mind. A lot of the discussion of complex numbers has to do with solving equations. That's why we care about this. Okay, in algebra, obviously, you solve a lot of equations. Okay, for example, if I wanted to solve the equation x squared plus 1 equals 0, I would have to know what a complex number is. If I don't know what a complex number is, then I would just simply say that there's no real solutions to the equation, right? That's what I was talking about up here. Now, no real solutions does not mean no solutions. Okay, like there are solutions to this equation. Okay, we just have to know what kind of numbers they are. The equation x squared plus 1 has solutions. We just have to be familiar with a complex number. Okay, it's just like if we wanted to solve the equation 2x equal 1. We would have to know what a fraction is, right? What a rational number is. If we don't know what a rational number is, then we would have to say that there's no integer solutions to this equation. Well, no integer solutions doesn't mean no solutions, right? This equation has a solution. It's just you have to know what a fraction is, okay? So that's why we are doing this, okay, is it all revolves around solving equations. If I have to, if I solve an equation, like I have to be familiar with the kind of numbers that would come up in the process of solving, okay? The next thing is I'd like us to get some practice working with some operations with complex numbers. Now, what I mean by that is just like your basic add, subtract, multiply, and divide. Okay, so let's take a look at problem 30. Now, whenever we add, subtract, multiply, or divide complex numbers, the end result should be written as a complex number. Okay, and that's how the book is going to want it. That's how my math lab is going to want it. Okay, make sure that when you have your answer, you have written that in the form a plus b times I. Okay, you're not done until you're in that form. Okay, let's take a look at adding and subtracting. Whenever you add or subtract complex numbers, it is very simple. All you do is you add the real parts together and then add the imaginary parts together. So like here, negative 5 plus 7 is 2, 3i plus 8i is 11i. 2 plus 11i, I'm in the form a plus b times I, and so I'm done. Okay, over here, it'd be a similar deal. Okay, 8 minus 13 is negative 5. Negative 6i minus 2i, make sure you distribute, that'd be minus 8i. Negative 5 minus 8i is in the form a plus b times I. A is negative 5, b is negative 8, and so we're done. Okay, how about if we multiply? So 8i times 13i, well 8 times 13 is 104. I times I is I squared. Now, I squared is defined to be negative 1, okay? So really what's happening here is I'm going to multiply 104 by negative 1, and that would give me negative 104. Okay, now the next question, is negative 104 in the form a plus b times I? Before you answer that, keep in mind that a and b are any real numbers. Okay, so if a and b are any real numbers, that includes 0, which means that, yes, this number is in the form a plus b times I. I could write this as negative 104 plus 0 times I. 0 is a real number, right? Now, we normally don't write plus 0, but we could, okay? So the point is that, yes, this number is in the form a plus b times I. And actually, every real number is a complex number. You guys have been working with complex numbers your whole life, believe it or not, okay? It's just the complex numbers that you have seen have always been when there has not been an imaginary part, okay, like b was 0. Now we're going to look at b being other numbers, like here's b is 11, b is negative 8, okay? Every real number is a complex number. Here's another example. Okay, the square root of negative 16 times the square root of negative 25. Now the first thing that you would want to do here is you would want to rewrite these two numbers in their imaginary form. Okay, so that's what I've done. The square root of negative 16, we've already looked at that, that's 4i, right? The square root of negative 25 is 5i. So now if I take 4i times 5i, well 4 times 5 is 20, I times I is I squared. I squared, again, is defined to be negative 1, so really I'm just taking 20 times negative 1 is negative 20. Okay, negative 20 is in the form a plus b times I, right? A is negative 20 and b is 0. So I can go ahead and circle that. Now, down here, I've done the calculation again, but this is wrong, okay? Like there's a mistake going on if a student were to work the problem like this. Let me point that out. So here's the square root of negative 16 times the square root of negative 25. What we've learned before in the chapter is that when we're multiplying radicals that have the same index, like we can combine that to a single radical by multiplying the numbers underneath. Okay, and so that's what I've done here. Gotten a single radical, and I'm multiplying negative 16 times negative 25 would be 400, and the square root of 400 is 20. Okay, so if I were to do the calculation like this, I get 20. So what's the answer? Is it 20 or is it negative 20? Well, negative 20 is what I have circled, okay? That is correct. There's a mistake going on here, and it actually happens right off the bat. So you cannot make this move that I did here right off the bat in getting a single radical, okay? You can only combine two radicals to a single radical if, let's see here, if both of the numbers are negative, that wouldn't be allowed, okay? And so that's a caution statement I have here. If a and b are both negative, the square root of a times the square root of b is not the same as the square root of a times b. Now, if one of these numbers is negative and the other is not, then there is no problem. Okay, like over here, if I were to, read this right to left, the square root of negative 1 times the square root of 7, I can write that as a single radical because both of these numbers were not negative. One of them is. Okay, but if both of them were, then that wouldn't be allowed. Okay, so that's why I had said, right off the bat, that the first thing that we want to think of in a calculation like this is the fact that we've got complex numbers. So that means that step 1 would be to rewrite these numbers into their imaginary form. If we did not do that, we would end up getting a wrong answer. Okay, we'll stop the video here.